AirHop is a leading provider of cloud-native AI automation and optimization solutions, driving network optimization for CSPs worldwide. Provide a very broad spectrum of use cases. We call our Optum use case. In the Ericsson EIAP platform, we're supporting today 9 different use cases. But today we're going to focus specifically on one of those, one of our energy savings use cases to help drive sustainability in wireless networks. So what is energy savings with MIMO adaptation? So essentially it's looking at a couple of different cases of how you can establish the network. One with all the antennas powered on, supporting high traffic load, but obviously that's done with the most amount of power consumption available. The other is moving the antennas into a low energy state, limited capacity, but the ability to lower the overall power consumption and still meet the required traffic demand at that time. So this is the goal, and what the energy savings rApp is meant to do is to optimize that ORU, TX, and RX power array of antennas in a way that adapts to that power consumption, essentially breathing in and out with the traffic load that comes in. So what does that mean? So what is it trying to do? So the main decision-making problem that this AI/ML solution is doing is saying, okay, I've got a couple of different antenna configurations available within the ORU environment, and I'm going to characterize those based on a couple of things, based on any traffic load that might come in. The first is going to be, what is the ability to meet that demand? So what's the PRB utilization? How much headroom do I have? How much capacity? So each antenna is going to have a certain level that it can support. So here in an 8x8 MIMO, you're going to have a lot of extra headroom with PRB capacity. The 2x2 MIMO, you're going to end up having saturated if the traffic demand gets a little too high. The other way to characterize it is based on user quality of experience. So we have a metric we'll call accessibility, and with the higher capacity antenna, we're able to always meet the user quality of experience. And when you move to the lower capacity antenna configuration, you're going to be able to most of the times meet that user quality of experience, but sometimes you're going to end up not having enough PRBs to support that, and you're going to have degradation in the quality of experience. And the last way to characterize it, of course, what we're trying to do is minimize the overall power consumption. So you're able to meet all the requirements in terms of capacity and user quality of experience, but you have at the cost of a higher power consumption with the higher antenna configuration. So move to the lower antenna configuration, you get much lower power consumption. Obviously, it's not always available to meet the overall traffic demand, and this is what the rApp is trying to do, is learn these and optimize the solution so that you minimize that power consumption and not degrade your user quality of experience. So how does this thing work? So we pump it with a traffic load, and we're going to show here how it's switching back and forth and how that affects both the PRB utilization, the user quality of experience with the accessibility, and then what the power consumption profile looks like. So here it takes a decision that, hey, we've got plenty of headroom. We can move this into a low energy state. We do that. Just up there, PRB utilization begins to go up because you have a much lower capacity antenna configuration, but power consumption comes way down. And then you make a decision that, hey, we're running out of headroom on our capacity, on our PRB utilization, so we make a decision to come out of low energy state, make sure the high load trap or antenna configuration is available, but this comes at the kind of cost of power consumption. So this is essentially what the rApp is doing in real time. It's taking traffic prediction models, and of course the real data is coming in from the network. So what does it mean in terms of the results that we get? So in the traffic profile that we were able to provide here, we're reaching about 25 to 30% power consumption gains with very minimal degradation in the overall user accessibility. And we maintain a fairly good headroom in terms of PRB utilization. So we have plenty of extra capacity if more comes in. And so we're able to check all the boxes in terms of making sure that the network is operating as we want it to. But we're actually getting a significant reduction in the overall power consumption and efficiency. So now we're going to take this to the field. We've done a field trial, and actually I'll have some things to point on this is going. For an operator customer, they had a 4x4 4G system that had two antenna configurations, a 4T4R and a 2T4R. Small typo there. 17 sites in this cluster, all connected to power meters so we can measure it. What we're showing here is basically over a 10-day trial, 3 days where energy saving was off to create a baseline, and then 7 days where we had PSMA operation. So you can see on the 4th day, we turn it on, and you immediately begins learning and reducing the overall power consumption and get a baseline for the rest of it as it's going along. So what does that mean? Kind of a nominal power consumption, but as soon as we turn it on, it comes down, and we're in that kind of 15 to 20%. Again, for this 4G system, that's kind of the amount of power savings you're able to achieve for that. So this is our energy savings for MIMO adaptation rApp. Kind of a good view of how this is doing. This particular trial is now full production. Here we're supporting about 48. We're now supporting more than 5,000 in the field today.